Okay, in this video we're going to talk about electric fields. The electric field is a concept which was developed to explain how force can be distributed throughout space surrounding a charge. Now, remember that in order to have a force, according to Newton's third law, it's always going to take two. So if all you have is just a single object out in the middle of space, then you do not have a force. All we're going to have is this field that we're talking about. Secondly, electric fields were an attempt to give some type of a mechanism to action at a distance forces, or as I usually explain in my classes, the non-contact forces. How is it that two things which aren't touching can actually exert forces on each other? Now, if you recall from last year, whenever we were discussing Newton's third law, we know that it's called the law of action and reaction. And at that time I asked you, what is an action? And it turns out that an action is just a force. So instead of saying that every action has an equal and opposite reaction, we redefine it as every force has an equal and opposite force. And I'm only pointing it out that, it's saying action at a distance, and then we tack on forces at the end to make it perfectly clear what we mean by an action. And so that's why we get away from that kind of language. Anyways, just an early attempt to explain how two objects can interact whenever they're not in contact. Now, what exactly is an electric field? I don't think anybody really knows just what an electric field is. What we do know is that you definitely can sense an electric field if you're in the presence of a strong electric field. If you've ever stood near a Van de Graaff generator, for example, that device that makes your hair stand up when you touch it. There's definitely something going on in the air. You can feel, the hair on your skin start to stand up, and, just something different about it. And that's in the presence of a strong electric field whenever you have large charges in the vicinity. The best way to explain what the electric field is it's like a stress. If you have a charged sphere in space, that sphere is touching the space around it. And when it does, it puts some kind of stress onto that space. And that would be this piece of space right here. And that piece of space will transmit the stress to that piece, and to that piece, and to that piece. So on out to infinity. There appears to be no end to this. Now, I only bring this up because this line of reasoning has an important consequence that goes along with it, and that is that the electric field, which we use a capital E for, the electric field moves at a finite speed. Now, what is that finite speed? It's going to be c, which is the speed of light, or 3 times 10 to the 8th meters per second. And that's going to be through a vacuum and through air, but of course through other materials the speed of light does slow down. Now, this might seem kind of strange, this idea that it places a stress that we don't really understand, but is it really an adequate explanation? And to that I'm going to say, well, of course it is. Just because we don't know how to visualize it precisely today doesn't mean we won't know how to visualize it precisely in the future. And my example for that is gravitation. Einstein's theory on gravity is not this action at a distance with a gravitational field, because we do talk about gravitational fields. Remember, we have a mass in space, and that mass can transmit its force, some force, without making contact. And how do we transmit force without making contact? We're using the field explanation, right? And so what is the stress placed on the space in the immediate vicinity of a massive object? Oh, well, the space becomes warped. it stretches out whenever there's a massive object nearby. And if you were to, the idea of the black hole, right? That's what happens whenever you have such a massive object that the space literally folds over back onto itself, and so not even light can escape. And so just because we don't know today just precisely what that stress looks like, if it's even possible to visualize it, it doesn't mean we won't in the near future even have a better picture and a better understanding of the electric field. So the electric field is going to be defined. That's what those three lines mean. The electric field is going to be defined by the force felt on a test charge divided by that charge, Q naught. So E is equal to F over Q naught. Now, the electric field is going to be measured in newtons per coulomb. The force, of course, is measured in newtons, and Q naught is measured in coulombs. Those are the SI units. And by definition, Q naught is a positive test charge. Now, sometimes for convenience, we rearrange this equation as F is equal to Q times E. But by definition, it's actually E is equal to F over Q, and that's how you'll see it on the AP equation sheet. Now, currently, we're talking about point charges. We will discuss electric fields due to continuous charge distributions soon, but right now it's for point charges. So, how do you get the electric field for a point charge? Well, the electric field for a point charge is going to be equal to the force exerted by a point charge. And what do we use for point charge forces? We use Coulomb's law. So that becomes K Q little q over r squared divided by little q. And that's because this q and this q are the same, so they're going to cancel each other out. This was our test charge. So remember, this is test charge. K is Coulomb's constant, so we can leave that alone. And this q we consider to be the source charge. In other words, it's the one that's creating the electric field. Now, when you have a force interaction, both charges are creating an electric field. Those electric fields interact with each other, and that's what creates the electric force between the two charges. So it is an interaction, and which one you call the source charge and which one you call the test charge is inconsequential in most problems. It really doesn't matter. So anyways, you cancel all this stuff out, and we get E for a point charge is just equal to KQ over R squared. Now, we have different ways of representing the electric field. Mathematically, we represent the electric field by this definition, E is equal to F over Q naught. If we're talking specifically about the electric field due to a point charge in space, we can redefine it as KQ over R squared. But sometimes we want a picture. And so in a picture, the electric field due to a point charge looks like this. It's going to be radially outwards if it's a positive charge. So this is a positive charge, and the electric field just points radially outward. If it's a negative charge, it's going to point radially inward. So the field lines are all going to be the same, but they point inward. For point charges, the lines are radial. The electric field is always going to be perpendicular to the surface. And if it's a point charge, it technically has no surface, but it's also how we end up with these radial lines. It's going to come out of the positive charges into the negative. And the direction of the electric force is always parallel to the field lines. Okay, so if you were to draw the force vector it could be in either direction here, like that. It could be straight up and down here, like that, for a charge which is placed here or here. Okay, so it just depends on whether or not there's a positive charge or a negative charge in that vicinity. But a charge placed in that electric field, it's going to feel force which is parallel to those lines. However, be careful, because if the charge, the test charge, is moving, its motion is not necessarily parallel to the field lines. And we're going to take a look at that in just a minute or two. The closeness of the lines determines the field strength. So you can see when you get very close to the charge that the field lines are also very close and the field is very strong. And that should make sense if we look at the Earth analogy. The closer you get to the Earth, the stronger the gravitational force is, or the stronger the gravitational field is. And so that, that should make sense. And then when you get further away, these lines get spaced out more and more and more so that the field weakens. And the last thing I want to mention is that positive charges move in the direction of E, or in the direction of the field line, and negative charges do just the opposite. Okay, so let's take a look at what we would call a dipole. And a dipole is basically two charges that are equal and opposite. So if I place a charge here which is positive and a charge here which is negative, then the electric field lines are going to come out of the positive charge and go to the negative charge. The easiest one to draw is going to be the one that directly connects the two, and it just points straight across. Now, I have these drawn as little spheres, and so the electric field line points perpendicular to the sphere. All right? And now there's a certain symmetry whenever you're drawing these, because they're radially outward from this positive charge, but they are radially inward at the negative charge at the surface. So that means there's going to be a charge pointing in there, one straight down here, another one that comes from behind, another one from behind, another one from behind, straight up, and then coming in that way. So there's going to be a certain symmetry whenever you have these equal but opposite charges. And so the field lines are going to be drawn something like this. And if I don't draw them perfect, I apologize, simply because it's not easy drawing on this tablet. And then these ones swoop way around like that. And then these two here, they just go out from infinity, come in this direction. This one goes out to infinity. Okay, so that's what it looks like whenever you have a dipole. Now, if you have two like charges, so we'll say it's positive charge, then the field lines are going to look like this. They're going to bend away from each other. And there's one place between these two charges where there is zero electric field, and that's going to be right here. This idea of what's causing the field lines to get pushed away is really important for our understanding of parallel plates and why the electric field lines point straight across from one plate to the other. And what I mean is this. So we have two parallel plates. We'll say this one is positive, this one is negative. And each one of these plates has charges all over it in a line. And these electric field lines, now if I look at this charge here in the middle, it's trying to create a field that goes this way, but it gets pushed this way, and on the other side that way. And this one's pushing that way, and that way, and that way, and that way. So ultimately what we get are these field lines macroscopically that point straight away. Now, if you were to zoom up to the microscopic level and get all the way down to the level of the individual charges, you would see that these electric field lines are not perfectly horizontal at that level. But at this level here, it is uniform, straight across from the positive to the negative. Now, let's revisit this idea of, what happens to charge which is inserted into this electric field, this external electric field. So if I have a positive charge which is moving in this direction, it's going to follow a path which is parabolic towards this negative plate. And the reason for that is it's going to feel a force that is constant in magnitude and always in the same direction. The force is going to be constant in magnitude, same direction. This is no different than looking at the gravitational field, where this is the Earth, and the gravitational field points straight down. You throw a baseball horizontally, so V initial is horizontal, and that baseball follows a path which is parabolic to the Earth. So the force is always going to be parallel to the electric field. That's an important point. Okay, so now let's take a look at electric fields of point charges. And this is, virtually identical to dealing with the superposition of charges when we're talking about forces. So I'm not going to get into a full-blown example here because you basically already know how to do it. But a typical problem would be something along the lines of you've got a charge Q1 here and a charge of Q2 here, and at some point in space, we'll just say, this point right here, indicated by that X, we want to know what is the electric field at that point in space. So if we call Q1 positive and Q2 we make negative, then what we're going to have at this point in space is an electric field that points radially away from Q1 along that line. So there's the electric field due to 1. And then we have an electric field which is radially straight down to Q2. So this is going to be the electric field due to 2. And we want to know what is the net electric field due to those two things, those two charges. So all we have to do is, again, we're going to do this in X and Y components, but E net is equal to E1 plus E2. But what we're going to do is break it up into X and Y components, because you should be able to see that E1 has a vertical component which is going to partially cancel E2, and then it has a horizontal component. So EX is going to be equal to E1 x plus E2x, but E2 is perfectly vertical, so that's going to go to 0. So EX is just going to be equal to, now this is a point charge, and so we have Coulomb's law, that's going to be K Q1 over R1 squared, and we're looking for the horizontal component with EX. And that's just going to be based on the geometry of the problem. We need theta, so this is probably going to be a cosine. And we could use this angle here if we want to do cosine. And so we'll just say this is cosine of theta, and you just have to go through and figure out what this angle is, because it's the same angle as this, right? If we have this distance and this distance, right? This is, this is theta right here. And then for the y dimension, what we have is E1 points up, so that's positive, and E2 points down, so that's going to be negative, so that's going to be minus E2y, E1y. So E net in the y dimension is going to be K Q1 over R1 squared sine of theta minus K Q2 over R2 squared, And there is no sine of theta here because it's completely vertical. If you wanted to use theta, theta would be 90. Okay, so for sine theta. And so that's basically it. I'm not going to take this particular explanation any further.